This series of videos looks at permutations and combinations and the difference between the two. Therefore, the first decision to each of the questions in this video will be whether the question is asking for permutations, so are objects being arranged in a particular order, or whether the question is asking you to find combinations, where you are choosing a number of objects from a set. Selecting the correct concepts for a question is an important skill to master. When you're in class, you know what is coming because one class tends to be about one specific concept the teacher has just introduced. It is therefore important to be exposed to a mixture of concepts within the same exercise. I encourage you to pause the video before each of the 4 questions in this episode in order to go through that decision-making process and to attempt the question. We can see in this question we are ordering people in a row, so this is within the topic of permutations. This first question is similar to one we covered in the first episode with a slight twist. This time all the boys and all the girls must sit together. I'm going to start by fixing the girls in the first 3 seats, and then for each permutation of girls there will be 4 factorial permutation of boys to go with them. There are 3 factorial ways the girls can be arranged, so 3 factorial lots of the 4 factorial. This is one specific situation. I can't slide the girls across one because this would split up the boys. However, the 3 girls can sit at the other end, so I need to multiply the number of permutations by 2 to get the total. This second situation will have the same number of permutations as the first, as it is symmetrically the same. This question does introduce the link between permutations and probability. As the probability of something happening is the number of outcomes of the situation you want to find the probability of, over the total number of outcomes, there is a clear link between probability and permutations. The total number of outcomes would be 7 factorial, as this is the number of ways we can order 7 objects in a row when considering the corresponding tree diagram. Therefore, the probability is 288 over 7 factorial, which simplifies to 2 over 35. The next question asks us to find a team of 6 from a set of 10 players. We are choosing a team, so the order does not matter. Therefore, we need to use the choose formula to answer this question. A team of 6 from 10 with no restrictions can therefore be chosen in 10 choose 6 different ways, which equals 210. For part B, there is an added restriction, so we can fix the first girl, and there are then 3 slots to be filled by the boys. Therefore, there are 8 choose 3 different combinations of boys to go with the first girl. As there are only 2 girls, we can list out the next situation, for which there will be another 8 choose 3 boys to go with this second girl. Therefore, in total, there will be 8 choose 3 times 2 lots of combinations, which equals 112. Note how this 2 can also be found by evaluating 2 choose 1, as this is a number of ways I can choose one girl from 2. Finally, to find the probability, we can use the same concept as previously discussed. Part A asked us to find the total number of outcomes, and Part B the number of desired outcomes, so the solution is 112 over 210, or 8 over 15. Just reflect for a moment on how this question is broken down for you. But in order to make the question more difficult, potentially they may skip straight to Part C without asking you for Parts A or B. It is therefore important for you to think about breaking a question down yourself in exams, asking yourself what you need to find first and second, or even third, in order to get to the final answer. Our next question again involves choosing a team, so we were looking at combinations and not permutations. For Part A, we have a restriction of needing 2 boys and 2 girls. For each combination of 2 girls, there will be 6 choose 2 combinations of boys to go with them. There are 5 choose 2 combinations of girls, so therefore 6 choose 2 times 5 choose 2 combinations in total, which equals to 150. Now we have more restrictions. As in the combinations we need to find, Anna and Tim need to be picked. I am therefore going to fix these in position. There will be 4 choose 1 lots of girls to go in a team, and for each one of these girls there will be 5 choose 1 lots of boys to also go in the team. Notice how we have to subtract 1 from the total number of boys and girls, as Anna and Tim are fixed. Therefore, in total, there will be 4 choose 1 times 5 choose 1 lots of combinations, which equals to 20. Again, we are asked to find a probability, having been asked to find the 2 parts of the fraction in parts A and B. Note that this question is 1 mark, so it should be as straightforward as writing down the answer without any method. Finally, Fred is the fixed person, and we need to find the number of combinations with either Anna or Tim, but not both. We can break this down into a team with Anna first. There will therefore be 4 choose 1 lots of boys, as we don't want Tim and Fred is already chosen. And there will also be 4 choose 1 girls to go in the final slot, as Anna is already in the team, so there are 4 girls left to choose from and not 5. If Tim is also fixed, then there will be 5 choose 2 combinations of girls to go with this specific pair of boys. We would then find the total combinations by adding these 2 together, as we want one or the other. The total is therefore 26. The final question is again similar to one in episode 1, but again there is a twist. We can see it is permutations, as we are arranging exams in an order. The twist is that no 2 out of the 3 papers can be together, instead of all 3 papers can't be together. Therefore, the first method and most straightforward solution I will look at does not subtract from the total what we don't want, as we will see later on. That will be quite complicated. I am instead going to fix the other 9 papers and then can see that there are 10 places for the first science paper to go in. The next science paper can go in 9 different places, and the third paper in 8 different places, as the number of places will reduce by 1 each time. This would result in no science papers being next to each other, as they would always be separated by another paper. It would also form a tree diagram, with 10 branches in the first representing the 10 places for the first paper, and 9 for the second column, and 8 for the third. We would therefore have 10 times 9 times 8 different permutations for the 3 science papers. We then need to consider that there are 9 papers that can be organised around them in 9 factorial different ways, and this would give us our final answer. I will now go through the approach of subtracting away what we don't want from the total number of permutations, as I think it is important to try to be consistent in our approaches to different questions. Firstly, there are 12 factorial different ways of arranging all papers. Next, I will look at the number of permutations with the 3 papers together, which is similar to a question we looked at where a group of people had to sit together. This is one situation with the 3 papers at one end. I can arrange the other papers in 9 factorial different ways next to them to go with each of the 3 factorial different ways the 3 science papers can be arranged. I will then multiply this by 10, as there are 10 different positions the 3 papers can go in if you consider sliding them across by 1 each time. I now need to consider 2 papers together. Again, I will fix the 2 papers at the beginning, and then put the third paper in between paper 1 and 2, as you can see in the diagram. There will be 3 factorial ways to arrange the science papers, and I can move the third science paper along to see that it can go in 9 different places. However, the problem with this is that when I move the science papers a long one, that is the pair of science papers, the number of places I can put the third science paper reduces to 8, so I can't just multiply out by the number of situations there are. This specific situation can only be repeated once more when the pair of papers is at the other end. I will now consider the pair of papers moved along one and add this to the total. There are going to be 8 places for the third paper to go, as discussed, and 9 places for this pair to go if we exclude the beginning and end places, and just move them across by 1 each time. This gives me 3 factorial times 9 factorial times 90 number of ways for 2 papers to be together if I add this to the number of permutations with the 2 science papers at the beginning or at the end. Subtracting all this away from the total number of combinations gives me the same final answer. I will give one more possible solution as it introduces an interesting concept that could be explored further for a piece of coursework, or if you're just interested in this. I can again think of the total minus what I don't want, but this time I am going to subtract the number of ways 2 of the science papers would be together without worrying about the third paper for now. Firstly, there are 3 choose 2 pairs of science papers to choose from, and 2 factorial ways for each pair to be arranged. Then, there are 10 factorial ways for the other 10 papers to be arranged, which will include that third paper. And finally, 11 places for this pair to be in if we again consider this pair of science papers moving across by 1 each time. However, in this solution, I will have subtracted the number of ways that the 3 papers could be together twice. For example, this specific permutation would occur when physics and chemistry are in the pair of science papers at the beginning and the biology paper is positioned next to them. The other permutation where this would occur would be when chemistry and biology would be in that pair of science papers, and physics would be arranged as the first paper before them. So the 2 science papers of chemistry and biology would be in the positions 2 and 3. If I have subtracted the 3 paper scenario away twice, then I need to add it back in once, as I only want to subtract it once. We found a number of ways the 3 papers could be arranged together in the previous solution, so I will just add it back in, and then we get the same final answer. This is known as the inclusion-exclusion principle, the idea where we subtract away too much, so have to correct ourselves. I encourage you to try a mixture of questions now to practice the methods covered in these 3 videos, as well as to practice your decision making when it comes to deciding which concepts are being tested.